Okay, so welcome to Apply Electricity course. So I'm Dr. Osman Al Hassan. So I'm going to solve the quizzes question for mathematical students. So that is MA 151. So I'm going to solve the quizzes question. Then with this, I'm going to start right away to solve questions, the quiz 1. So in quiz 1 was based on chapter 1 to chapter 4, right? So we start with the first question. So we have question 1, which is a battery of 40 volts supplies a current of 5 amps and produces 72 kilojoules of what energy. How long does it take to produce this amount of what energy? So we have first one, question 1A. So you have to find the time it takes to produce this amount of energy, which is 72 kilojoules of energy. So first I have my energy E, which is equals to 72 kilojoules, which is the same as 72 times 10 to the power 3 joules, which is energy is going to be equals to 72,000 joules. So you have 72,000 joules, that's the energy. Now the voltage, which is giving us 40 volts, then we have a current of 5 amps, right? 5 amps. And we are asked to find the time. So when it comes to energy first, so we know that power is going to be what? The rate of what? Energy, right? So power is the ability to do work, and the work done is the same as energy. So we are going to get power to be equals to energy over time. So if we make energy the subject, so we get power times time. That will give us the energy. And then power, as we know also, that power can also be calculated using what? The current times what? The voltage. So if I know the current and voltage, the product should give me the power. So we replace this power in, let's say, equation 1, right? Equation 1 here. So we have energy to be equals to the current times voltage times time. So this is going to be the formula for calculating energy will be equals to this. But since we are interested in the time, so I'm going to label this as equation 2. So we make time the subject. So time here will be equals to energy over the power, which is just current times voltage. So we get here to be 72,000 over the current, which is 5 amps, times what? 40. So this will give us, so give me So this 0 cancel 0. Then I'm having 4 here is going to, okay, let me just use my calculator so I get it very fast. So I get 72,000 divided by 5 times 40 here, so you get 360, right? Get 360 seconds, which is, you can change this into what, into minutes, and that is going to be, meaning 360 seconds divided by 60, which will give you 6 minutes. So the time here is 6 minutes. So it's going to take 6 minutes to produce the 72,000 kilojoules of energy. Now we go to question B. We are done with 1. Now we move to the next part, which is 1B. Here a current of 6 amps flows for 3 minutes. How many electrons are being transferred? So here, if I have a current flows for 3 minutes, and we know that current is what, the flow of what, electrons, and then which means the flow of what, charges. Once you have electrons, or electrons are what, they have charges. So with this, if I have a current flowing for 3 minutes, I should be able to get the charge, right? The quantity of charge. And we know current, as I said, is going to be what? The flow of charges with respect to time, meaning the flow of charges within a specific time. So we have charge over time for current. So once I have my charge, then later I will try and get the what? The electrons, number of electrons that are going to be transferred. So this will give me, charge will be equals to current times time. So with this, let me get the charge. We have the current is 6 amps times 3 minutes, right? Which means 3 minutes with 3 times 60, so that you get it to be in seconds. So you have this, you multiply all of this. So you can see here that you can have this, there is 0 here. Trying not to use my calculator. So 36 by 3, 36 by 3 will give you 108 here. Right, so we have 1080 coulombs of charge. So that will be the quantity of charge if you are having a current of 6 amps that is flowing for 3 minutes. Now let's get the number of electrons. So when it comes to this, we are going to make use of the fact that if I have 1 electron, right, 1 electron is going to contain a specific amount of charge, right? It's going to contain a specific quantity or magnitude of charge. So 1 electron, normally it contains 1.60 times 10 to the power minus 19 coulombs of charge. So it's even given in the question. So once I know this, then if I'm having what, 1080 coulombs of charge, then how many electrons can I get? So meaning I can come here, put X here. Since I know 1 electron will have this quantity of charge, which is 1.60 times 10 to the power minus 19 coulombs. Then I have now how much will 1080 coulombs per charge gives me. So how many electrons will I get? So with this, we cross multiply. So if you cross multiply, we realize that I'm going to get the number of electrons here to be equals to now 1080 divided by 1.602 times 10 to the power minus 19. So this will give me 1080 in inverse, so 1080 divided by 1.602 times 10 to the power times 10 to the power minus 19. Minus 19. So we are going to get 6.742 times 10 to the power 21 electrons. Right? So the amount of electrons that we get here is going to be 6.742 times 10 to the power 21 electrons. Get this amount of electrons. So that is it for the first question. We go to the second question. Okay. So we go to the second question. So the question, I have question 2. Okay, let me even make it now. Right here, question 2. I have question 2. Calculate the currents in figure 1. So we have figure 1. This is my figure 1. So we are to calculate the currents in this figure. So if you look at figure 1, you can see that we have a circuit diagram. And with this circuit diagram, you can think about this in terms of the number of branches we have, right? So here we have, let's say, 1, 2, 3 branches, right? And each of these branches that we have, you can decide to assign current to each branch. Then you can use branch current method, right? So there are a lot of methods that you can use to solve for the currents in figure 1. So the method that I'm going to be using will be network reduction, right? Which is based on the concept that once I have only one voltage source, then it's being connected to resistors, and then I can simply reduce these resistors so that I'll end up having a voltage source and then only a single resistor, right? Or a single resistance, right? So with that resistor, which is going to be the equivalent resistance, right? So I'm going to use network reduction. So I'm going to reduce this, okay? So and then to do the reduction, meaning we have to make use of what? Series and parallel connection. So if there's series connection, that means I can find the equivalent resistance, The same for what? For parallel connection. So starting with this, so using network reduction, so I'm going to have this one. So the first one, I have this. So I'm going to look at the resistors, how they are connected. So if you look here, I have 5 ohms and then 2 ohms. You can see that they are connected in series, and then 4 ohms and then 6 ohms, they are what, in series as well. So I can reduce that part, so I can have my resistor, mean the whole of this. Now I'm going to reduce that so that I'll get the equivalent resistance. So since 5 ohms and 2 ohms are in series, so meaning you get the equivalent that is going to what, the sum. So meaning 5 plus 2, that will give me 7 ohms. And then the same for what, the other side as well, meaning 4 ohms plus 6 ohms, that will give me 10 ohms. Then I have my 3 ohms, then my voltage supply, which is 30 volts. So with this, I can now look at what, this 7 ohms and then 10 ohms. Then they will be what, they are connected in parallel. Why? Because here, if you look well here, there is 7 ohm resistor in that of 10 ohms. They are connected end to end, right? End to end. So one end will connect to the other end, then so they are what, in parallel. So if they are in parallel, meaning I can get the equivalent resistance there, meaning of 7 ohms and 10 ohms to be equals to, you take the product, right, meaning 7 ohm by 7, 7 by 10, then over the sum, plus, let's say 10. So we get 70 over 17, 70 divided by 17, that will give me 4.1, let's say 18, right, ohms. So we get this for the, so we have this one. Then so meaning I can come and sketch a new circuit diagram where I have my 430 volts. Then with this, I maintain the 3 ohms here. Then I replace now the 2 parallel connected resistors with now their equivalent, so I get it to 1.18 ohms. So you can see that after doing this, you realize that now you have 3 ohms is now going to what, in series with what, 4.118 ohms. So I can get the final equivalent resistance, which is what we call the overall equivalent resistance for this, will be just the sum, meaning 3 ohms plus 4.118 ohms. So this will give me 7.118 ohms. So I can finally sketch the final equivalent circuit which is going to just a single resistor, which is the equivalent resistance, and then I have my voltage source. So I can have current here, which is what I here, the main current, or you can call it the total current, right? Total current. So once I have this, to get this current, right, because we are asked to find the current in the circuit diagram. So current here will be equals to, meaning using Ohm's law, right? Using Ohm's law, the current is going to be equals to, meaning the voltage supply over the resistance. So the resistance here is the equivalent resistance. So we have this to be 30 divided by 7.118, and that will give me what? So that should give me, the current to be equals to 4.215 amps, right? 4.215 amps. So I have this as my main current. So this is the current that is going through here. Okay, this is my I, the total current. You can see that once it gets here, and you have a node here, which is a junction where two or more components are connected. So I have my main, so I can now indicate at the junction here is going to be what? Divided, or is going to be, because these two branches are in parallel. So I can label for this branch maybe I1, and then the other one to be my I2. So now I can calculate for I1 and I2. So here I'm going to use voltage division rule, right? So here using voltage division rule. Sorry, not voltage, current division rule. Current division rule, then I can get I1 to be equals to 1. Okay, so it's going to be equals to, so I can come and also even indicate this one here. So here this is just going to be the equivalent circuit. So I have my I1, because here the same current is passing through 5 ohms and 2 ohms, so which is 7. So that's why you can come and use this one. Or if you don't want, once we understood this, there's no need. So now I have my current that is going through this one, right? So to get this, we take the other resistor, right, which is 10 ohms. 4 plus this will give you 10 over the sum of the resistors which are connected in parallel. So I have 7 here, and then this 10. So 7 plus 10 times the main current, or the total current, which is 4.215. So I get 4.215. So this will give me, this is going to give me the I1 to be equals to 2.479 amps. Then my I2 is going to be equals to, again the same thing, we are finding I2, we take the other resistor which is connected in parallel with the I2, the current that is passing through I2 that is passing the other resistor. So we get here is going to be meaning 7 over again then the sum of what the resistors which are connected in power, which is 7 plus 10 times again the total current or the main current. So here we are going to get this 1.736 amps. So this is what for question. So this is for question 2. Okay. Now we move to question 3. So question 3. So I'm going to have my question 3 here. Now for question 3, you have to find the power dissipated by the 7 ohms resistor in figure 2. So here is my figure 2. We have to find the power dissipated by the 7 ohms, meaning this one here. So to get the power, as you know, the power dissipated by a resistor is going to be equals to the current which is passing through the resistor square times what? The resistance. So here again there are various ways you can solve this. There are various ways you can go about solving this, right? So I mean the current that is passing through the, let's say 7, or maybe make it 7 ohms current that is passing through the 7. This is just labeling. And then we have our 7 ohms resistor. You can label it this way as well. Now to find this current, which is a current passing through 7 ohms, you can use a number of methods. So I'm going to be using nodal analysis to solve for this one. Nodal analysis. Right. So we have nodal analysis. So with nodal analysis, we tend to assign current to each branch. So like we assume that you assign current to the branches. So the current, let's say we have how many branches? We have one here, we have another one here, then we have another one. So if you assign current to this branch, so I'm going to label here, let's say I1, and the current which is going through this branch I'll label as what? I2, and then this one as what? I3. So once I've done that, you can see that with this I have, because of the voltage source here, I'm assuming that the current is originating from the voltage source, so 24 ohms. So I'm making the direction to go this way. Likewise, there were 9 volts, so current originating from. Now they all go what? They will meet at what? This junction, then they will sum up, then they will give you I3, which is going through 2 ohms. So after this, indicating the current, I can apply Kirchhoff's law to node, right? To node A. Let's say I'm going to label here A, node A, the junction here A. So we apply Kirchhoff's current law at node A. So once I've done that, then I'm going to write the equation. That means that I1, you can see, is entering the node, so the sum of current entering the node will be equal to the sum of current leaving. So I1 is entering the node, the same for I2, so I1 plus I2 should be equals to, and only I3 is leaving, so it equals to I3. Right. So with this, I can now get the current. I've gotten the current, so let me get now the this the voltage in terms of what? Resistors, right, that are in each branch. So I1 here, I have within this, because one current is going to be passing through each branch, so meaning one current, the same current is passing through the 3 ohms and 4 ohms here. So the voltage here, sorry, the current I here will be equals to, in that case, the voltage, which is 24 minus the voltage at node A. So here I can label here node A2 is having the voltage, right, VA, over the resistors in that branch. So we have 2 of them, which is 3 ohms plus 4, the other one, which is this one. So we can see that we've taken the potential difference, and meaning 24 minus the voltage at node A, and then over the total resistance in that branch. So now plus, now I2, you can see here we have only one resistor. So we have what? Our voltage source, which is 9 minus VA over 7. Then that will give us, that will be equals to, again for I3, we have again only I3 is going through 2 ohms. And then the current, you can see now based on that, is originating from what? VA. So here we get VA minus VB. We tend to ground the other node, this node here, you ground it, and then here we label it B, and then the voltage at B, because it's grounded, is going to be 0 volt. So here VA minus B now be equals to what? 2. But since VB is 0, we can write this now, simplify this a bit. So 24 minus VA over 7 plus 9 minus VA over 7 to be equals to VB is 0, so it is just VA over 2. So we have this. If you were to solve this, I'm not going to go all of this and then go and solve it. So we can solve this by what? Multiplying both sides by 14. Multiplying both sides by 14. And then if we were to do that, we end up getting 48 minus 2VA plus 18 minus 2VA equals to 7VA. Equals to 7VA. Now you group them. So take the VA, you send them across, so we get here to be 48 plus 8, that will be 66. That will now be equal to 7VA plus what? 2VA plus 2VA, right? So which is going to give me 66 equals to 11 VA. So we take VA will be equal to 66 over 11, which will be equals to 6 volts. So we have VA to be 6 volts, but remember we are interested in the current that is going through 7 ohms. And this 7 ohms current, you realize that the current 7 ohms here is the same as what? I2. So which is going to be equals to, like I said, which we already stated here, and I2 here was what? This one. So I'm going to come here to write 9 minus VA over 1 over 7. So this will give me this to be equals to 9 9 minus 6 over 7. That will give us 0.429 amps, right? 0.429 amps. So we get this for, okay, but we are not done yet. We are interested in the power. So power will now be equals to I 7 ohms square times R, which is what, 0.429 square, times R here, which is 7. So this will give me 2.88 watts. So we get 2.88 watts. So that is the answer you get for this question. So let me try and make this one, highlight the answers. So for the power dissipated, we got 1.288 watts, and then that was for question 2. Now question 3 rather. So question 2, what do we get the I2 to be equals to 1.736 amps. Then I1 was 2.479, and then I, which is the main current or the total current, we got 2.157 amps. Then we go to question 1. We calculated the question B, which was the number of electrons that have been transferred. We got it to 6.74 times 10 to the power 21 electrons. That was for 1B. And then question 1A, we got 6 minutes, right? That is the time that is going to be taken to produce 72,000 kilojoules of energy. So